So we can write any complex number z in polar form r times e to the I theta p, where theta p, remember, is the principal argument. But then we're free to add 2 pi times an integer. Okay, so you can always, to any angle, you can add 2 pi or 4 pi or minus 2 pi, and you get the same angle. Okay, so this, whatever the value of m, this represents the same complex number. Now, when we find the nth root, what we do is raise this to the power 1 over n, where n is an integer. So we do that to both sides. Okay. Now, when we do that, then m divided by n times pi added to an angle doesn't give you the same complex number unless m is equal to n. If m is equal to n, then effectively you're just adding 2 pi times 1. So you're adding the same thing. So basically, this is why there are precisely n roots of nth roots of a complex number z, because m can vary from 0, 1 up to n minus 1, and all of these cases will give you numbers which are not multiples of 2 pi. You'll get 2 pi, you'll get 0, you'll get 1 over n, 2 pi over n, then you get 4 pi over n, and so on, up to when you reach n minus 1 over n times 2 pi. The next case would be n over n times 2 pi, which is 1 times 2 pi. Okay. Now, you could choose m to be 0, 1 up to n minus 1, or you could choose any consecutive integers. You could also choose, for example, m equals minus n over 2 if n is if n is even, or you have to do n minus 1 over 2 if it's odd, and so on, and then go minus n over 2 plus 1, and so on. The advantage of that is, and then up to, you have to do n of these, up to, the advantage of doing this is that you then get some which are negative values and some which are positive values. So then you can choose things so that this argument overall is a principal argument. It's between minus pi and pi, but it doesn't really matter. It's fine if you just want to choose m from 0 up to n minus 1. This will become clear when we do some examples.